I wanted to close out this year on a more positive note, so today we're talking about fusion. More specifically, fusion power. It was the power source of tomorrow, yesterday, and it still is. Fusion gets a bad reputation for constantly being just on the horizon of discovery. It's always 30 years away, presumably hanging out with the cure for cancer, robotic body parts, jetpacks, and millennials' dreams for homeownership. So today I'm looking at whether or not fusion deserves that reputation, why fusion is so difficult to do, when we can expect it, and how it will change our world. Fusion isn't something that happens very often here on Earth. There are a couple of exceptions, but those almost invariably involve several hundred square kilometers of a very bad day. But off of Earth, out in space, we see fusion all the time. It's actually pretty much all we see, because fusion is the process that powers the stars. The extremely basic explanation of what fusion is that it's a nuclear reaction in which two atoms fuse to become a heavier element. This all starts with hydrogen. It was the most common element in the universe. Eventually, it clumps together, creates gravity, brings in more hydrogen, squishes itself very tightly, ignites, becomes a star, and starts turning into heavier elements. Helium, lithium, and so on. If you think about it for a minute, there are some pretty profound implications of this process, but however you want to look at it, fusion is already a big deal at a cosmic scale. And fusion could be no less important for humanity. If we harness it for power generation, we could use the most abundant element as fuel, hydrogen, with no radioactive or carcinogenic byproducts. It would change everything. Which provides a hell of a motivation, right? But last I checked, this isn't the center of a star or a nuclear explosion, so how can we control that process to go from this to this? I do need to explain a little bit about what fusion is and how we might do it on Earth. This will be the Cliff Notes version because the bulk of my formal training is in how to tend a bar, so spouting off a ton of fusion technobabble at you seems a bit like, I don't know, leading an IBS support group into the wilderness for a campfire dinner of chili and room temperature hot dogs without knowing the difference between poison oak and a maple leaf. That is to say, irresponsible at best. But I think I can give you a pretty good understanding if we just go through three things: fusion, fission, and iron. Both fusion and fission are nuclear reactions in that they involve atomic nuclei, which is the place in an atom where the protons and neutrons live. Atomic nuclei are surrounded by a cloud of electrons. In a nuclear reaction, you almost always start with two atoms, you cause the reaction, and you get out two different atoms. Sometimes these reactions take tons of energy to start and release very little. Sometimes it only takes a tiny bit of energy to start and they release megatons as a result. In terms of creating usable power, the practical difference between fission and fusion power are which atoms they will be using for their reactions. If you want to create super heavy elements, the reaction takes a lot more energy than you get back. But if you can find huge, unstable heavy elements, like, say, uranium, that are already put together, then it doesn't take much to break them apart, which gives you a net return on your energy investment. This is fission power. Lighter elements, like hydrogen, still take a lot of energy to mash together, but more energy is released in the process. This is fusion power. The dividing line between giving energy for creating an atom and taking energy for creating an atom is iron. Iron is an element so stable that whether you want to break it apart or fuse two together, it's going to take you more energy than you'll get back. Below iron, you get more energy for sticking things together. Above iron, you get more for breaking them apart. More practically speaking, fusion and fission both have trade-offs. The big advantage of fission is that it's easier to do. The universe already put a bunch of energy into making these ultra-heavy elements, which is why they're so rare. The fuel is harder to find, but it's easier to use as a power source. It's so easy, in fact, that if you don't properly control the little eager beavers, they will rapidly react faster and faster until you get an explosion or a meltdown. And once you get the reaction that you want, you're still left with unstable byproducts that themselves are constantly releasing energy as they continue to break down in the form of radiation. With fusion, the fuel is so abundant that it forms clouds and literally falls from the sky. If you can stick it together, you will get more energy out than you put in, and you'll be left with helium, which you can use to give yourself a silly voice. Which, all things considered, is a really stupid way to use helium, but the fact that you can use it to give yourself a stupid voice does make it the polar opposite of fission's byproduct, which you can use to give yourself lymphoma. Unfortunately, the disadvantage for fusion is that starting a reaction is a lot harder than a fission one. Fusion happens in our sun because it's got a few dozen times Earth's gravity, and it's 14 million degrees, which is not a temperature you run into on Earth, ever. We do have a saying on Earth, though. When somebody is said to catch lightning in a bottle, it means that they've done something almost impossible, or so far beyond expectations to be thought of as impossible. You can't catch lightning in a bottle? Of course not, hence the expression. But catching lightning in a bottle to fusion is child's play. We're talking about putting a star in a jar, which is possible, you just need a hell of a jar. The reason it takes so much energy to start a fusion reaction is twofold. For one, atoms interact with each other through their electrons, the particles outside the nucleus that exist as kind of a shell. To get fusion to work, we have to get the nuclei to interact, which means we have to get rid of that outer electron shell. If you heat something up enough, it starts to lose electrons from its outer shell, and it becomes a form of matter called a plasma. Which brings us to our second problem. Protons are positive, electrons are negative. With one of each, hydrogen atoms carry a neutral charge and are kind of ambivalent about running into each other. With its electron gone, our hydrogen is now winging around with a positive charge. Because similar charges repel each other, our two positive hydrogen atoms are about as likely to go together as a cocktail server at a dive bar and the saying, "Thank God it's Friday." It's so difficult to make atoms fuse together that in the sun, it takes your average hydrogen atom about 1 billion years to form into stable helium-4. Which gives you some idea of the problem here. If we don't want to wait around for a geological age for fusion to occur, we're going to need temperatures more than 10 times what we'd find at the center of the sun, more than 150 million degrees. Then, once we do that, we have to build a box that will keep our mix of distilled cosmic death from spilling out and melting half the county. Also, that box has to allow some energy transfer, or else what's the point of all this? It has to be able to feed some of that energy back into itself to keep the reaction going. The fact that we know how to do this is just, holy crap, humans are awesome. The most common approach to doing this is the tokamak, a toroid, or spherical containment area, lined with superconducting magnets. We can give the walls of our reactor a strong enough charge that the atoms inside will avoid the walls more than each other. This makes the atoms more likely to fuse together, with the added bonus that our walls don't melt. Besides using just ridiculously high temperatures, we're also going to make this easier by going for an easier reaction. Instead of hydrogen to helium, we're going to use isotopes of hydrogen, deuterium and tritium. We're using isotopes because turning hydrogen into other kinds of hydrogen takes less energy and is more likely, in that hydrogen prefers to become itself over helium. And by prefers, I mean in the quantum mechanics sense, which I'm not even going to try to explain here, but there are labeled links down in the description just in case you're the kind of person who wants to go learn about double slit experiments and boxing up maybe poisoned cats that might be fine. You'll have to check. The thing is, the toroid, the magnets, the hydrogen isotopes, all of this has been the primary research path for fusion power since the 1950s. Even the name we use for our theoretical power donuts, tokamak, is more than 60 years old. So this ain't new. Why is everybody so excited? Well, Flash Gordon had a jetpack and now this is a thing, so maybe it's time to take another look at some of this stuff. Now it's not just that we think we know how to build one of these, we're building one. And not just some small proof of concept thing to make sure that fusion is possible without the world's second worst donut filling killing everyone in the lab. Right now, 35 countries are building the ITER project, which translates from Latin into English as the way. The ITER project is the world's biggest fusion generation experiment to date. Think of it as the International Space Station of power plants. Even with the giant cost of the ITER project, $25 billion and counting, we won't see it fire up for the first time until 2025, which is only 5 years. In fusion terms, that's right around the corner, but that's also just the start of the project's run. Unfortunately, usable fusion power is probably still another 15 to 30 years out. It's just that this time, we're talking about a delivery date, not an optimistic best guess. To be perfectly fair, the whole perpetually 30 years over the horizon thing isn't really the fault of scientists and engineers who've been tirelessly working on this technology since the 1950s. Frankly, we do a piss-poor job with scientific literacy and science reporting in our world today, which is not a new problem. Those past instances of the scientist who cried fusion probably went something like this. A scientist announces some kind of breakthrough that gets us closer to making fusion power work. A press release is written up. Somewhere in there, someone asks, "So, what does this breakthrough mean for our progress for fusion? When can we expect to be living in the future already?" To which the scientists respond, "Well, I mean, we still have a lot of problems to work out on the..." Come on, sound bites, just give me your best guess. Ballpark. Best case scenario. Sure, I mean, if XYZ thing happens that solves all these problems that we have no idea how to overcome, and also we don't discover any new incredibly difficult problems while we're trying to create conditions 10 times more extreme than the center of our sun, 50 years? 50 years? That long, really? Maybe 30 years if some sort of miracle breakthrough happens. So 30 to 50 years, at the earliest. Got it. And then a headline comes out that says, "New wonder power, 30 years away. Take that, you dirty commies." The point is, it's not really been the scientific community that's been misleading us per se. Even so, how is our world really any different than it has been in terms of scientific reporting? Besides the fact that your average journalist is less likely to wear a news cap, less likely to use the word commie, and less likely to have a penis, we still live in a world of politics, profit, and a general mishmash of bullshit and stupidity. So why should we believe that this time fusion really is a generation away? Well, two reasons. The first major reason is that most of the solutions we need to make fusion work have gone from ifs to whens. And I don't mean that there's a general certainty that some problem will get solved or a discovery will be made. I mean that the machine is due to turn on in 5 years. The ITER project isn't the first huge fusion experiment. It's the last. ITER's goal is to provide the first net positive power yield from a sustainable fusion reaction. The reason I'm still saying fusion is 20 years out minimum and not 5 is because that 2025 date is the beginning of the project. The plan is to ramp up their experiments over a decade until they're running a sustainable plasma fusion reaction around 2035. That might seem like slow progress, but we're talking about a $30 billion piece of equipment that's unique in the world. Careful, methodical advancement is really the only option here. But earlier I said there were two reasons to think that fusion's coming soon, and the ITER project is just one. The fact that scientists are now referencing calendars and not just vague future decades is a good sign, but they've also been joined by another group entirely: private industry. There are now half a dozen startup companies looking to be the first to roll out a workable fusion generator. These aren't small tinkering startups run by somebody's uncle who's trying to build a perpetual motion machine. These are big operations. TAE Technologies has raised close to $1 billion in venture capital from fund managers who aren't typically known for their harebrained schemes. There's Commonwealth Fusion Systems with $200 million in funding and a couple of hundred of the greatest minds at MIT working for them. General Fusion has also raised more than $200 million, the lion's share coming from Jeff Bezos. Lest you worry, the Billionaires Club is solely focused on space. The point is, the private sector thinks it can get a standardized fusion power system into the world faster than the ITER project, hopefully as early as 2040, which, if you're keeping score, is 19 years away. And 19 years would be great. The sooner the better. Because there's a laundry list of things that fusion makes possible that currently aren't. Enough that it'll probably be called the fusion age. If, are we still doing that? The largest and most immediate impact of fusion power would be on our environment. Fusion not only eliminates most of the carbon footprint of energy generation, it could actually result in a net reduction, depending on what we do with the power. I should mention that while fusion is definitely the clean energy solution of the future, when you look at it from the perspective of, holy shit, the world is on fire, 2040 is still a long way off. We still have to get our world to 2040 in some semblance of working order so fusion can help us keep it that way. But provided we can figure out other ways to stop being such a dick to nature, here's what we get for our troubles. We'll be able to grow food wherever we want, basement, high-rise, whatever. We can make gasoline out of the air. It makes interplanetary travel more practical, and it completely changes our entire economy, just to name a couple things. Fusion will have such a massive impact on our society because, big picture, Everything humans do is about energy, getting it, trading it, and what we can do with it. Physically speaking, humans aren't really very well equipped for dealing with our environment. Without our technology, humans would spend most of our time yelling, "I'm cold, I'm hungry, bear's eating me." So we invented tools, because this beats this. And we lured in beasties with tasty snacks so we could borrow their strength to exert our will on the world, because this beats this. And eventually we invented machines to do our work even faster, because this beats this. In each instance, we increased the amount of force at our disposal, the amount of energy. Sure, technology is all about efficient application of force, the right tool for the right job and all that, but it's also about capturing a larger and larger amount of force to use in the first place. The combine doesn't work without its engine. The plow doesn't pull itself. Technology is really just a thing that allows us to direct the energy in fuel at something we want to do. At a macro level, this is why fusion is such a big deal. The fuel is everywhere, and the energy we get out of it is mind-boggling. Every kilogram that we feed into our fusion reactor releases many, many, many times the energy contained in a barrel of oil. Almost overnight, having enough power is pretty much never a problem again. Getting all that power to go where we want to use it now becomes the far bigger issue, but that's a good problem to have. This means that battery technology suddenly becomes incredibly important, but it doesn't mean that you have to ditch your diesel tractor in the meantime. Gasoline is a decent way to haul energy around to wherever you want to use it. That's why we use gasoline. And we could still use it, all without paying a premium in feelings of guilt and impending doom. Right now, when we burn gasoline or other hydrocarbons, it releases water and CO2. But we can also take CO2 and water and make gasoline. It just takes way more energy to do than you'd get back out of the gasoline when you again burn it. But so what? Sure, that's the reason we don't do it right now, but with fusion, we have plenty of non-polluting energy to spare. We have a lot of CO2 to spare as well, it turns out. Just to put this in perspective for a moment, when I say fusion is a fundamental change in nearly everything, I mean that it makes gasoline refineries clean the air. Any process or plan that's been held up because the energy costs involved to make it not economically viable is suddenly back on the table. Speaking of the table, take farming, for instance. The thing is, we already use fusion to grow our crops. That's what sunshine is. But as I said, the problem with fusion is getting that energy where we want it. The sun drenches us in photons every day, but they're really easy to block, which means if we want to use them for farming, we have to put our crops outside. Also, we don't have any control over the strength or wavelengths of that light, and it's only on about half the time. But it's free, so we don't really complain. Our crops are also touchy about pretty much everything: soil, pests, temperature. So we drench them in chemicals and can only grow them in certain climates. If it's the right climate, but there's a stupid, useless forest in the way, well, that's why we invented the axe, or, fire. So right now we're choking our waterways with chemical runoff, killing the absolute shit out of biodiversity and habitats to clear pasture land, and then we have to stick the crops we grow on whatever go faster machine we want to use to bring those crops from where they grow to where you live, farting out the toxic souls of dead dinosaurs the entire way. And this is the cheapest way to grow our food, all because we get that free supply of energy from the sun, a supply that can be completely eliminated by a simple cardboard roof. But put that star in a jar, and we can transport all that power using, wires. Wires are great. They can drill through roofs or wherever. Roofs are great for holding up lights. Lights that we can tweak for maximum efficiency and leave on all the time. Stick some walls around this sucker and we can even control the climate inside. Put all that together and we can build a 40-story grocery store that sells food on the bottom floor that it grew on the upper 39. Depending on how anal you want to be about it, no pests can get in. We can filter the water that comes out. And the dinosaur souls stay right where they are. Also, now the price of your banana doesn't include the cost of transport. It does include the cost of fertilizer and the power to keep the lights on, but both of those things are now way cheaper too. All that space between our cities and towns that we currently call farmland could change its name to park. Fusion power will have such a fundamental effect on the economy that it's impossible to provide any summary that comes even close to being inclusive. There is one thing I can say with some confidence though. And that is, if we're still using our current economic system when we get fusion, we probably won't be using it much long after. Economics is a squishy pseudoscience at the best of times. Fight me. But we've already seen the effect of automation massively increasing productivity while crushing the cost of labor. It's led to huge economic gains for this tiny section of people who own everything. Fusion power will only accelerate this process, and it's hard to believe that 12 billion people will sit through another explosion of economic prosperity that only benefits the richest million or two. But if the fusion economy is at all equitable, the 2040s promise to be a great decade. And as this new year turns over, it's nice to be looking at a bright future. We just have to get there.